Awesome. Let's see if I'm live. Usually it takes like 30 seconds. So I'll just wait before I start speaking. Awesome. It didn't take 30 seconds. I'm already stammering. I'm trying to get stuff out of the way. Now I'm all set. Hey everyone. Welcome back to the deep learning book study group. This will be the last in the series. I swear my eyes are red because of the shampoo and not crying from reading all this math. But we'll be going through the remaining last two chapters. And before we get started, one quick announcement. I had promised to start a study group for this book. I've read this like a third of the way through already. I usually prepare beforehand. This will start in about 2 weeks. I have been in touch with the authors and they'll be joining for the kickoff session. So hopefully it'll be on a Saturday, but depending on them, it might be on a weekday. And then it'll continue on the same time as this meetup. So if you're interested in learning about NLP, just stay tuned for that. That should start in 2 weeks. And the the paper reading groups that I used to do for a while. If you remember that, well, that's awesome. But I used to do paper reading groups for a while, and those were insanely popular for some reason. I'll be bringing those back as well, and they will hopefully also be on a weekend, probably a Friday, just to accommodate. So just stay tuned for that. You don't have to do anything; it'll just start by itself. Just those two announcements. Now we can get started. We'll be going through the chapter 8 and 9 of this book, and I'll be wrapping up on convolutional networks, not on RNNs, not on practical methodology, or not on applications. I didn't intend to cover part three anyways, but the reason for this is RNNs aren't really used so much anymore. Andre Karpathy even said that he skipped RNN's lecture. He's been posting on YouTube lately, if you're not aware, but he skipped that because it's not so impactful nowadays. So for that reason, I'll wrap up on CNNs. If you all have more questions, just tweet at me. If like a lot of you have questions, I can just do one more Q&A session if needed. If not, I can just answer them on the internet. So either ways, I'm happy to take any questions. For the study group, this will be the same as always. So for the first half or like the first few minutes, I'll summarize everything from the book. I'll summarize different things. I'll give an overview, and then we'll go look at the book and different topics. As a warning, I'll be suggesting a lot of topics that you all can skip from these two chapters just because of the relevance in my mind. It's totally up to you if you want to read them or skip ahead. So let me continue with this. Quick recap from the last live stream. Regularization stands for any modification we make to a learning algorithm that is intended to reduce its generalization error, but not its training error. Which means regularization is any trick you apply to a model or while training a neural network to help it generalize better beyond the training data set to help improve its accuracy, so to speak. We learned about different regularization. We learned about parameter norm penalties, which is basically adding an omega, the headphone symbol, as I kept saying. We learned about L2 parameter regularization, L1, and we also learned about constraint optimization. We didn't discuss dataset augmentation in a lot of depth. There was some mathematical definition around it. In reality, you're probably just importing from albumentations, and that's all that matters there. If you don't know, albumentations is a really popular image augmentation network, and there is also an NLP org, I believe, framework. So both of these are what you would end up using. In case you didn't know, it's called NLP org, and the first one is albumentations. So instead of looking at the math in depth for all of these, just check out those frameworks instead of data augmentations math at least. Now coming to chapter 8, it talks about optimization, and they start by talking about what is learning and what is optimization. So when you're learning in a neural network, you are optimizing the cost function, which is optimizing the overall end goal. By that I mean what you're really optimizing are the weights for the cost function. So let's say you care about making more money through optimizing your food delivery business. So that's the way you are optimizing. But when you are just working on an optimization problem, you are just working on, let's say, hey, I want to deliver this in the fastest time possible, so you are optimizing just that direct function, which is the distance or delivery. And if, like me, you are looking at the food delivery apps and you're judging your delivery person for being so slow, even though they are on time, you know what I'm exactly talking about. So that's what matters to business against different settings. Shashidhar is saying he'll keep joining the future live streams. Thanks for that. But for this book, it will be the live stream, last live stream. You're welcome to watch the remaining, the older ones, and the future ones, at least for now, will be on this book. So on NLP. Still, thanks for joining, and you're welcome to watch the previous ones and just leave comments. I always read all the comments on all the videos. They also talk about empirical risk minimization. They give a mathematical definition for it, and then they talk about batch versus online methods. So batch methods, it's sort of the I would suggest, if you're getting confused with the definition in the book, just skip that. But when they're talking about batch, they say it looks at the whole data. By that they mean they're assuming you already have the entirety of the data set, and what you're doing there is you're just working with the entire data set, creating small batches from it. When you're working with online learning, you have a stream of incoming data that you end up working with. So basically, online learning and looking at the entire data set is what they're referring to. And I don't consider it a direct contrast, because even for online learning, you might be applying batch learning. Let's say your data update comes every few days. In reality, what you might have is a Spark cluster that updates your script sometimes. You might have different things that are deploying all of this stuff on a regular basis. So, and that also might still require batch learning. So if you have that knowledge, you might be able to distinguish this. If it's confusing to you, just skip the fine nuances. After this, we talk about the algorithms for different learning methods. They talk about SGD. So in this slide, what I've done is I've given basically like a one-line summary of all of them. Stochastic gradient descent involves computing the gradient and updating the weights. Momentum computes velocity, which means it takes into account, and they have like a very rigorous definition of it. But what momentum does is, to avoid getting stuck in a local minima, it accounts for the previous direction of the weight upgrade, and it adds that as a correction. So basically, you have a factor being added based on the velocity, as they call it. They talk about NM, and I'm not even going to try to pronounce what the extended form of this is. But the difference here is the gradient is updated after the velocity is upgraded. From there on, they talk about parameter initialization, and then they give the justification that normally, if you initialize all layers with like in a similar fashion or the same numbers, there won't be a lot of learning, right? Because like they all start from the same point and they're very symmetrical in that way. That's the exact word from the book. So what I would recommend is they also define a lot of these. They give a few definitions, but what you should be looking at is, I like PyTorch. I don't know the exact corresponding module in Keras. I'm sure there is. I'm sure I can even Google it right now. But you should be looking at torch nn.init, and you can look through all of these. Some of these initializations are introduced in this chapter. Kaiming Ho is one of the most common ones. Javier uniform is also one of the most common ones. Javier normal is also used a fair amount. And this one is actually introduced in the book, as I understand. Chiming uniform is the one I was referring to. So this is chiming her. It's also known as her initialization. HE, it's pronounced as her. Just fine. That's a fine nuance I happen to know. So you can look through this module of PyTorch or the corresponding one in Keras if you want, instead of the definition. After this, they talk about adapter learning rates, and they introduce different algorithms around it. I'll be actually reading through all of these later on, so we'll go through the algorithms together. But Adagrad talks about it. Doesn't talk about what it does. It individually adapts learning rate of all parameters. But sorry, it does that by scaling all parameters with respect to the gradient. So that's what Adagrad does. What RMS prop does is it modifies Adagrad to perform better in non-convex settings. Adam is adaptive momentum, and it's basically RMS prop with some momentum. What's really going on is they're calculating the square of the gradients, but in simplified fashion, it's RMS prop plus momentum. Let's see. I also wanted to point out Torch Optim docs. So again, we will look through all these algorithms individually, but I would also encourage just go through torch.optim and read how they're like actually used, the different parameters you can change inside of PyTorch, and you can see that here's Adam W, this pass Adam. There's a lot of them. They also talk about LBFGS, which is I see it's there in PyTorch, but I've never used this, and I don't know where this is exactly useful. So I didn't, as you can see, include them in the slides here. By the way, a side note here, yesterday I had hosted some of the like really, really top Kaglers. So their consensus was Adam is pretty good. Just use Adam. And that video is up on the H2O AI YouTube channel. You can see my face, but this is the name of the video. So you can just go to H2O's H2O.ai's YouTube channel, and that's the first video in the live panel. But the general consensus from at least the best Kaglers was Adam is pretty good. Just start there. After this, I'll summarize the last chapter that we intend to cover at least very quickly. So CNNs, as they start, is the most parallel to human brains, and they define this by saying I has a focus region called fovea. Everywhere else is blurry inside of the image. If you've sat across that machine where you put your chin and it does this adjusting, you hear all those weird noise, and you see that blurry road, that's exactly what's happening inside your eye. You basically have all of this area which is not in focus, and then your eye is very sensitive inside one region called the fovea, where the image is really sharp. So if you wear spectacles or corrective lenses, you would know what I'm talking about. The brain is responsible for interpreting these eye movements, and the authors parallelize this with filters. So they talk about how cascades are similar to eye movements. They talk about 3D images and how they are created from two eyes, which basically means the slight difference in the angle of both eyes creates this 3D image inside the head. There's no direct parallel for CNNs in them, but this was just another biological factor they mentioned. So this somewhat parallelizes in the sense that you have filters that work in CNNs, and you have this cascading which is parallel to that, and the filters focus on different areas, hence fovea. These are pretty cool because they have something known as parameter sharing. Kernels share the weight and are the same kernels being applied across all layers. And CNNs are simply neural networks that use convolution in place of general multiplication, at least in one of the layers. So this was the formal definition inside the chapter. And this was the summary of both the chapters. Now what I'll do is I'll switch screen sharing and I'll highlight different things I intended to inside the chapter. So they talk about optimization by stating that deep learning algorithms involve optimization in many contexts, and they say, for example, you're performing inference in models such as PCA, which also is an optimization problem by itself. I'd skipped this, but it was heavily introduced in the matrix multiplication chapter. And they said this chapter focuses on one particular case of optimization where you're finding the parameters of theta of a neural network that significantly reduced a cost function j of theta, which typically includes a performance measure evaluated on the entire training dataset as well as additional regularization terms. They also talk about how learning differs from pure optimization. I alluded to this in the slides already, but I'll just read through this. Let me minimize that. They say we care about performance measure P that is defined with respect to the test set and may also be intractable. So there's no direct way of sometimes optimizing it. We therefore optimize P only indirectly, and we do that by reducing the cost function. So many times, and this is like again stepping out of the book, but what you end up doing is as an engineer, you're helping a business, and the business, like any business, wants to make maximum money. So depending on where you're working or what product they're building, you're trying to maximize their income depending on whatever problem they're solving. And of course you can't ask chat gpt to just solve that. So what you end up doing is you try to figure out how that's expressed mathematically, what problem that becomes. Usually it's like a very complex, but simplified, it just becomes a function you're trying to optimize. So like I said, let's say you're a food delivery app, and what you really care about is how can you get food to the customers in the fastest way possible and also maximize your profits while doing that. So I leave it as an exercise for you to figure out how to do that. But that's a parallel example to this. Next, they say the cost function can be written as an average over the training set, like so. So j of theta is equal to error over the entire data, where the loss function is a function over f x comma theta and y. This is the predicted output. So f x comma theta is a function that predicts the output when given the input x and data over the distribution. Y is the ground truth. After this, talk about empirical risk minimization. I'm going to skip this. It's straightforward. It's a simplified formula. At least I was able to understand this really quickly. Next, they talk about surrogate losses. So they say sometimes the loss function you actually care about, let's say classification error, is not the one that can be optimized efficiently. So what happens is you end up creating a surrogate loss function which acts as a proxy but is easier to optimize. I'll keep scrolling and keep pointing out different things. Now, one thing to recognize, and if you've been following along or if you've read in the book, I at least have come so far where I can understand that this is the gradients being calculated of the cost function. So that's what I'm somewhat able to read this function without losing my mind. And these are being calculated by taking the error over the log of the predictions, and the gradient of the log is being calculated. And if I scroll above, they do mention somewhere that the log uh, error is being optimized. So I was right in that fact, and just wanted to point out that it's somewhat easier to read these functions now. They mentioned that the standard error of the mean estimated from n number of samples is given by sigma divided by square root of n, which is the standard deviation. And the denominator shows that there are less than linear returns to using more examples. You can remember this function. We had learned about this a few chapters ago, but they just mentioned that the standard error of the mean is the following. I didn't remember it for the record. I pointed out the difference between batch and online, the nuances that they use in the book. So I'll skip past this, but if it confuses you, just skip through this. My point was that usually online learning also involves a lot of batches. So your data is usually coming in, maybe let's say images or whatever you're working on. You would end up creating a lot of batches of those. So what I'm scrolling to now are the different optimization algorithms. Again, the reason I highlighted this, I just wanted to rant about this for a second. But here they say ill conditioning. Some challenges arise when you're optimizing convex function, and some of these are ill conditioning of the Hessian matrix. This is the most common numerical optimization or convex problem described earlier. I have no way of remembering this, and I couldn't understand this. And after this, they also talk about, hey, you should be able to recall that the second order Taylor series expansion of some cost function is like so. I cannot recall, and I don't think you should be able to recall this, or you wouldn't be joining the study group at least. But just to point out that no, these things aren't intuitive, and I don't recall them making sense anywhere. I personally am not interested in remembering these because I don't think these are helpful. They're just helpful for my case. These are just useful when you're working with mathematical derivations or stuff like that. So the long story short of that is this: they skip through a lot of sections when you're in the last few chapters. They talk about local minima and how your model or how your optimization algorithm can get stuck in saddle points or other flat regions. They also cover gradient clipping and gradient explosion. So they say sometimes in the loss landscape, you have these areas where your weights can suddenly fall off a cliff, as they say. The reason I wanted to talk about this is I've said this many times, but this space is multi-dimensional and it's not usually 3D like they show here. So there's no real way of knowing if this is happening, and usually you are like only observing very small. So there are two cases: either you observe very small changes and your model doesn't fit, or your loss is negative infinite. And either either ways, when that happens, you have other problems to deal with. But anyways, they do point out that sometimes this might happen. Realistically it doesn't, and for those cases you might want to use gradient clipping. Both of these are straightforward functions to apply in both either APIs that you end up using. So again, I'm skipping past these. And they do mention vanishing and exploding gradient problems here. Okay, I'll keep scrolling further. I don't see any questions in the chat yet. So now what I'll do is I'll go through these individual algorithms and just read them along with you. So they're called basic algorithms, but they're really the ground of training almost all models that we end up using. So let's look at stochastic gradient descent update. Here's the algorithm. So they say learning rate schedule is E1, E2, and so on and so forth. I pointed out the panel I'd hosted yesterday, and again, the general consensus there was the best learning rate scheduler is cosine learning rate with some warm up. But again, for warm up, I couldn't get everyone to agree on something. Again, it's the general answer there was it's just experimental and you try what works best for the models. In the book, they say towards the end, you would like to decay your learning rate towards a smaller number because the general understanding is as you train a model, you might want to reduce the learning rate as it reaches the optimum, which is true for cosine as well. Because if you remember, cosine follows somewhat of this shaped graph. So the rate does decay. Realistically, you're only like following perhaps this much of its area. Let me highlight with red. Maybe this area. So what it looks like is, let's say this is 0, and I don't know, this is like 10 to the power minus 6, something like that. So it only see like a very small decay like that. You never end up like taking it actually down to 0. So that's what they're referring to. You have a learning rate scheduler, and your learning rate might keep changing as you're training the model. They say you initialize your parameters with theta and you set k to 1 while you don't reach the target loss function, which usually is the criterion. You keep training the model. So they say you sample a mini batch of M examples from the training set. Sitraka is saying, ha, I don't understand to what you were responding. Um, but they say you keep sampling mini batches of M examples from the training set and you have the corresponding targets. For those, you compute the gradients and you do that by using this function where you sum over the loss function for all the examples, calculate its gradient divided by M, which is the number of samples in your mini batch. And then you upgrade your weights like so. So you subtract your learning rate and the gradient estimate. And then you keep iterating like so. So this denotes a for loop. This is the counter of the for loop. And this is the weight update step. This is how the gradient is being calculated here. This was SGD. After that, they talk about momentum. So what momentum ends up doing here is you basically have a velocity term, like I kept saying earlier. To point out in the graph where they show, the main reason for using this is if you look at the black arrows here, if you keep upgrading your weights with SGD, they might just your gradients might just explode in the sense that they might just go to the extremes of this graph. Let's say it keeps following these points. Let me use green to not confuse everyone. But let's say it keeps finding itself on these extreme points. To avoid that or to avoid that very drastic update, what momentum does is it accounts for the previous weight upgrade. So in the sense that if your model is being forced to, or sorry, your gradient is being forced to jump to the extreme right, you keep in account that the previous update was from this direction and you subtract by that term. So what you end up doing is, let's say you subtract by this velocity. So your real update becomes, I'm running out of colors here and I don't know how to add another one. I'll use red. Please excuse that. But your real update then becomes somewhat of a smaller one in that case. And as you can see, the red line denotes here the updates with momentum. Let's look at the algorithm for the same thing. You have a learning rate, you have a momentum parameter alpha. You initialize your parameters with whatever function you end up using, and you keep training until you reach the stopping criterion over all the mini batches. The main difference here is you are also computing the velocity update with every step. How is this being done? You have a term for velocity, which is also accounting for it, and then you're also factoring in the gradients. So it's similar to upgrading the gradients. Velocity is also upgraded like that. You just use the previous gradients to account for that. This is momentum. After this, they talk about Nesterov momentum. Sorry if I butchered that up. Simply put, it's NM momentum. But in this, there's an additional term used for velocity. So here's the algorithm for that. And if you just look closely, what's happening here is the velocity update. Sorry. The interim update happens before upgrading the gradients. And then the gradients are calculated, after which the velocity is again updated. So simply put, the velocity update happens before the gradient update. Ashad says, awesome explanation, momentum elaborated nicely. Thank the authors, I'm just repeating what they taught me and I'm just summarizing it. So I don't have anything to do with that. I just read this book ahead of you, that's all I did. So that is SGD with NM or Nesterov momentum. Again, just to repeat myself, the velocity update happens before the gradient update. This might also be a very cool interview question for research positions or research scientist positions. Although if you're appearing for those interviews, I don't understand why you'd be watching my videos. Uh, After this, they talk about how you should initialize weights. And I just wanted to highlight one term. You want to break symmetry between different units. And they justify this by saying if two hidden units have the exact same activation function connected to same inputs, then these units must have different parameters. So after this, they introduce a few of these. And I already pointed out what they are. You can read through the book. I'm not going to elaborate on them. So again, I'm scrolling towards the next function. So what we'll discuss now are the algorithms with adaptive learning rates. The first one is Adagrad. Adagrad individually adapts the learning rate of all model parameters by scaling them inversely proportional to the square root of sum of all the historical squared values of the gradient. So basically, the weights are updated in an inverse proportion to the gradients. RMS prop modifies Adagrad to perform better in non-convex setting by changing the accumulation into an exponentially weighted moving average. Here's the Adagrad algorithm. So you have a global learning rate. Here, there's not a scheduler being used because I wanted to point this out because these have a way of upgrading the learning rate. You initialize the parameters and you have a small constant. One thing to note, you're also accumulating the gradients here. So you compute the gradient as usual, and then you accumulate the squared gradient. Again, this is a way of showing dot product, which basically means you're doing a squared upgrade. Why did they use a dot product? Most of the times, this is a vector. And by vector, I mean a matrix. So np dot mat or np dot dot is what you're thinking in your head. The update is calculated like so. So division and square root applied element wise is the update for the weights or the parameters. And then it's added in this case. Why? Because there's a negative term here. I'll just repeat myself because I went over a lot of things. So the learning rate is constant because it does get adapted through this approach. You compute the gradient using the same using the same fashion like you had been. You accumulate the square gradient by taking a dot product with itself. You compute the update, which is delta theta, and it is added because there's a negative term while you're changing theta. So what you're doing is you're taking the learning rate and you're dividing it by the constant we had defined plus square root of r, multiplying that with the gradient. RMS prop, if you look very closely, is very similar and just a few terms change here. So here you use a different a different constant, I believe, rho, which is a decay rate alongside the global learning rate. So if I scroll past back up, you might not see any row element here, but that's being added here to accumulating squared gradients. Again, scrolling up to point this out. Please focus here if you can. I'm looking at this function of accumulating gradients, squared gradients. And when I scroll back down, you'll see a row function being accounted for here. That is the key difference. Then we come to Adam, which is the most common one being used. At least the panel I pointed out earlier was in heavy favor of this. The name Adam derives from the phrase adaptive moments. It is perhaps best seen as a variant on the combination of RMS prop and momentum. So here they show RMS prop. Am I mixing stuff up? Yes, I am. Again, so when I download it, the PDF sometimes it mixes up the algorithmic stuff. So we had already looked at RMS prop earlier, and this one is RMS prop with NM. Here is the Adam algorithm. So it's being a bit mixed up. Sorry about that. But if you download the PDF, it ends up mixing these things. So you have the step size E. They have suggested defaults. I wouldn't use these. What I would use is the library defaults. So if you're using PyTorch or FastA or whatever library, just trust the defaults here. You have exponential decay rates for moment estimates, rho 1 and rho 2. And you require a small constant for stabilization. You initialize the parameters of the model. Usually you are downloading pre-trained weights. So you can think of this as a substitute to that. You initialize the first and second moment variables, and then you account for a time step here. So you keep account of the timestamp and you update the first moment estimate and the second moment estimate. And then you also end up correcting the biases by updating them throughout these loops. And using these, you calculate the gradient update. That's the Adam algorithm. If this felt rushed, I would encourage you to read through at least the algorithms in this chapter. That's the only thing I would encourage everyone. So if you want to skip this chapter, just read through all the algorithms. It'll take 1 hour max and things will make a lot more sense. After this, they talk about approximate second order methods. I'm going to skip past all of these. And they also talked about LBFGS, which was the first time I have ever heard of it. And then I did just see it in PyTorch, but I haven't ever used it. So I'm scrolling past all this. LBFGS, limited memory BFGS. After this, they talk about batch normalization and introduce some of its concepts. I did not find anything new here. So my suggestion would be you can also skip this if you are interested. So that was all I wanted to cover in this particular chapter. That's the end of chapter 8. And chapter 9 overview is going to be a little shorter as well, because I didn't find a lot of things that are worth highlighting here. So I'll define how convolutional layers are being used here. They use this really cool analogy, and this was very refreshing to read. So they say, suppose you are tracking the location of a spaceship with a laser sensor, and your sensor provides a single output x of t. T is the timestamp. You get different reading from the laser sensor at any instant in time. Suppose that your laser sensor is somewhat noisy, and to obtain a less noisy estimate, you would basically average all the measurements. So to do this, you use a weighting function, not weight, but time weight in the sense of average, where A is the age of measurement, and you summation, or basically you do an integral of the following term. This operation is called convolution, and it's simply denoted like so. They create analogies with kernel and feature maps. So they say in convolutional neural net terminology, the first argument, x, is input. The second argument, weight, is the kernel. And the output is sometimes the feature map. And I'll point out visually what these are. There are some mathematical properties which you can look into. I just read these ones and I definitely am not going to remember them. But they say we have flipped the kernel relative to the input, and this denotes a commutative property. If you look closely, I star k can be flipped like k star I inside this example, or inside this denotion, mathematical denotion or mathematical formula. That's just the highlight I remember. Of course, if you want, you're welcome to read through it. They talk about how to efficiently implement this in different libraries, and at some point they did mention MATLAB. But again, all of this is very very efficient in today's libraries, so I didn't really pay attention there. They showcase how these weights are being shared in the CNN model. So inside a fully connected network, you would have all layers being, or all units being connected to all different units. And then they show different representations along how CNNs work and how these are tied weights. In the sense, you end up using lesser of a memory footprint because you use these kernels that are being convolved over the input. After this, they talk about pooling function, and they showcase the general structure of a CNN layer. So they say you have an input layer which goes to a convolutional stage, which goes through an activation function, after which you finally have the pooling stage. And this keeps getting repeated quite a few times. That simply is a CNN model. And inside of pooling stage, they had this cool example where they showcased number 5 being detected. So let's say you see a large response in a particular unit here. Max pooling would just pick this. So it would pick the maximum response. And this would hopefully tell the model that hey, this is number 5. And similarly in this other example as well. That's how simply CNNs work. So what I'm going to do now is I'm going to again switch screen sharing, and I took these notebooks from FastAI. Sorry, not notebooks, Excel sheets. And this visualizes how convolutional networks are being used. Let me paste the link in the chat in case anyone wants to find these. But I just took the liberty of grabbing these from the following repo. Ayushman is saying hello. Ayushman is a computer vision expert. He's a high rank Kaggle master. I don't know why he's watching this. He should be hosting this live stream. I think he just pops in the chat to troll me from time to time. I think that's all he does. But wanted to point out this link. So just go to FastAI's course repo. You'll get this Excel sheet there. This shows you how convolutional layers actually or models actually operate. And this is completely implemented inside of an Excel notebook. You have these different filters that have all of these weights, and you have this input of number 7. What's happening inside is you take this filter, this matrix, if you may, and if I look here, you'll see it's being operated with all of these numbers. So this number, which I messed up, let me cancel that and let me zoom in a bit. If you look at the formula, which I can't zoom into, you'll see that this is being derived from the multiple of these two. And then if I move one number over to the right, you'll see it's coming from the next number. So what's happening is you're taking this filter and you're moving it right from the leftmost corner, one by one, over to the rightmost corner. So if I look at the last number here, and if I highlight the formula, let me cancel all the changes I'd made. So if I highlight the rightmost number, you can see that it was derived from the operation in the rightmost edge. You do this for all the numbers. Ayushman is saying, when are we doing the next competition? I don't know, Ayushman, you tell me. So you do this for all the numbers, and you basically take this filter from all of the numbers across all of the input. So here the stride is 1, because if you see this number and the next one, if you see again, I'll point out, please pay attention to what's being highlighted in the left uh, portion. So what's being highlighted here? This comes from this number, and then you move just 1 to the right. If this was 2, or if this was the next column, the stride would have been 2. But here the stride is 1. So you multiply this filter with all of the input, and this gives you one layer. And then you do it again with another filter, and that gives you something else. So that's another layer inside the neural network. You get this first convolved layer, and then you have more filters later on, which keep doing the same thing over and over again. So now these two filters, the first one gets multiplied with this, the second one would get multiplied with this number, which is coming from the other filter. Both of these get added, and the second convolutional layer comes up. Sanskar is saying hello. Hello, Sanskar. After that, what you do is you take the max pool. So if I highlight the function here, this is taking the maximum of all these four numbers. Let me prove that point. So 5 is coming as a maximum of these four numbers. So what happens after the first few convolutional layers, or the first few steps of the filters being applied? You would want to reduce or somewhat pick the activations from these numbers. So apply a pooling layer. It could be max pooling, it could be whatever. And now you are left with 1/4 of these. Then you could again do this one more time, or this would then become the output. You do this a few times, and then you use the algorithms we had learned to update the filters. Hopefully, after you do that correctly, your model would be able to tell you that this is the number 7. That is convolutional networks. Quickly summarizing one more time, you have this input, you have all of these filters, which get multiplied with this input one by one, depending on the stride, or in lesser numbers. Then you get more layers, which are again convolved, and you make sure you account for all these numbers by multiplying the filters with both of them and adding them. So you can see that this number or this matrix is being multiplied with both these filters. After that, you apply a max pool layer or a pooling layer, from where you pick or you reduce this by 1/4. So what you end up doing is selecting the maximum number of four of these four, let's say, and you would say, okay, this is 8, and you can see that there's a 8 somewhere here. So these are the internals of convolutional models or convolutional neural nets. Priyanshu is saying hello. Hey Priyanshu. Priyanshu is one of the best tabular experts that I've met. He's absolutely insane on tabular Kaggle problems. That's all I wanted to highlight in this chapter as well. So just wanted to give credit to the FastA repo. So thank you FastA for having these Excel notebooks that I could simply use. And that was all I wanted to highlight in the last chapter that I wanted to cover. So I'll suggest this homework one more time. Sebastian Ruder has this awesome blog on most of these algorithms, so I would encourage you to read it. It's on ruder.io, and the title is Optimization for Deep Learning Highlights in 2017. I would suggest try implementing these algorithms, or at least look at the API if you can. So the TensorFlow Keras and the PyTorch API. Check out the study group repo. I will update it once I figure out how to do that. First link in the video description. And consider subscribing for the future meetups. In 2 weeks, I'll be starting the NLP study group, as I said. And I'll also be bringing back the paper reading groups. So I'll be summarizing different research papers, and hopefully that might be of help to you. I am not going to cry because I've cried enough reading the math. I'm just joking. I'm being hyperbolic, but again, it was quite challenging, at least for me, to read this book. Hopefully, you found some value. The playlist is going to stay up on the channel. So thanks if you read through this, and we'll get back to more books that are really parallel to Kaggle competitions or stuff like that. Axel is asking what days are the sessions of the study group. I'll live stream every Saturday at this time, so 8 a.m. Pacific for the NLP study group. And for paper reading, I'll probably do Friday because Saturdays and Sundays are booked out. So Sunday, I'll always live stream something about Kaggle, and Saturdays will be a study group. That's what I do on weekends. All right. Thanks, everyone. Hopefully, you found this study group useful. Maybe you'll enjoy reading the papers. I at least wanted to read this once, and now we all will have an easier time reading through the papers. That was my intention. I don't see any questions. I don't see any comments. So if you have any questions, you can join the H2AI community. Let me point the link out, and you'll be notified of any future upgrades or any future meetups I'll be hosting. Head over to this link, introduce yourself there if you'd like. Everyone is welcome to join that. If not, I'll see you tomorrow or next week. Thanks for joining.